This is the first in a series of videos about phase transitions. In the last set of videos, we talked about how intermolecular forces can explain the properties of liquids. And in this series, we'll talk about how intermolecular forces explain the transitions between different phases, solids, liquids, and gases. So we're going to start out with a question that I think will blow your mind. And that is, how does a puddle evaporate? Take a second, think about it. It's not as obvious as you think. How do liquids usually get from the liquid phase to the gas phase? They boil, right? Is a puddle boiling? Nope, definitely not. Definitely not at 212 degrees Fahrenheit. So if it isn't boiling, how then does the liquid get to the gas phase? There's something else happening. And we call that something else vaporization, which is the general term for the phase change from liquid to gas. So there's some way for liquids to get to the gas phase without being hot enough to be at the boiling point. So let's think about what sort of phases keep liquids in the liquid phase. Let's return to the picture we drew at the very beginning of this chapter about liquids and solids. We drew solids, liquids, and gases, and we thought about the force holding them in the condensed phase as the pull. And that was the intermolecular forces, the attractive forces holding those molecules close together. And the only way that they could escape the pull of the intermolecular forces was with a push from kinetic energy. Adding heat, adding energy to the system allows the particles to move faster and to escape the attractive forces holding them together. So it takes energy to break those attractive forces. We want to break the intermolecular forces holding these together, and the same is true for breaking actual bonds. This requires energy input. So let's think about a distribution that we talked about way back in the gas law chapter, the Boltzmann distribution. Boltzmann distribution plotted number of molecules that had a particular kinetic energy or velocity. So we used it to talk about gas molecules. Let's use it to talk about molecules of a liquid. So the same general shape is true. If you take a temperature, which is a general snapshot of an entire batch of molecules, you end up with a shape that looks a lot like this. Looks a lot like a bell curve, but it has a particularly long tail at the right end. And let's say that this is at a fairly cool temperature. The amount of kinetic energy it takes to escape from the liquid into the gas phase is going to be way over here. It's going to be a pretty high amount. So we'll say this is the minimum energy required to break the intermolecular forces and escape into the gas phase. So if we look at this fairly cool temperature liquid, the area under the curve represents the number of particles with enough energy to escape. And we can see that that area is very, very small at this temperature. There's not very many particles that can escape, but it's also not zero. There are always a few particles in the liquid phase with enough energy to escape into the gas phase. So now let's draw a slightly higher temperature version of that curve. So let's say this one is at 450. So now, as we've increased the temperature, the curve has shifted over towards higher energy, and it has flattened and widened. And now the area under the curve that's past this minimum kinetic energy includes this red area and this blue area, and it's much larger. So as we increase the temperature, that's the energy input we need to provide the energy to jump from liquid to gas phase. So we call this energy the enthalpy of vaporization, or we can call it delta H vape. And this number is always going to be greater than 0. And remember, that's because we need to put energy into the system. So that's an endothermic change that we're doing. And endothermic heat flow is always a positive number. So delta H of vaporization has units of kilojoules per mole. And we can use this number to find the amount of heat we have to put in to change the phase simply by multiplying by the number of moles of substance that we have. That gives us the heat Q in kilojoules of the phase change. More on that towards the end of the video series. Okay, so we've talked about how to go from a liquid phase to a gas phase. So if we increase the amount of energy to go from a liquid to a gas phase, that is called vaporization. And that is how puddles disappear. But we can also go the other way. We can decrease the amount of energy to go from a gas to a liquid, and that is called condensation. And remember when we talked about Hess's law and the fact that enthalpy is a state function, we talked about flipping. If we flip a reaction and to go in the opposite direction, that is just like multiplying it by -1. And everything that we do to the equation, we do to the delta H. So if the enthalpy of condensation is the opposite, the reverse process of vaporization, that means it's like taking the enthalpy of vaporization and multiplying it by -1. So these phase changes are simply the opposite direction of the same process, and so one of them is the opposite of the other. But these two processes don't occur separately. One doesn't occur at hot temperatures and the other at cold temperatures. Both of these are occurring simultaneously. So let's do an example picture to get a feeling for what this looks like. So let's say that we have a cup of coffee. Cup of coffee is nice and warm, almost boiling, burning your mouth as you're drinking it. There are going to be a distribution of particles with different amounts of energy for one particular temperature of coffee. And we know that some of them are going to have very, very high energy. So we'll draw those with red. There's going to be some particles with particularly high energy, and if they reach enough energy that they are above the minimum kinetic energy required for this vaporization phase change, they will vaporize and jump into the gas phase. And with these phases, with these particles of the gas phase, some of them may cool down, they might touch the wall, or they might feel a breeze from outside, and they might cool back into the liquid phase and condense. So these processes are happening at the same time, simultaneously. And so if we were to put a lid on this container so that our coffee stays warm, lid, in case that wasn't clear. If we put a lid on the container, both of those processes are happening at the same time, and we reach a state called a dynamic equilibrium. We'll talk more about this in the chapter about equilibrium, but this is like a preview. Dynamic equilibrium happens when the rate of vaporization and the rate of condensation, the reverse process, are equal. So it's not that they're both stopped, it's that they're both moving at the same rate. The same number of particles that are going up into the gas phase is equal to the number of particles coming down into the liquid phase. And so when we put the lid on, and so we have a closed system and we reach equilibrium, we can measure something called the vapor pressure, which is going to be an important feature of liquids. So we can write that as P vape. And this is, as we see in the picture, pressure exerted by vapor, which is in equilibrium with a liquid. And it has to be in a closed container at some given temperature. We can measure the vapor pressure at this container once we have a lid on and we've reached equilibrium. In the next video, we will talk about the difference between vaporization, which we've just been talking about, and boiling, and how those processes are similar but not the same.